we recommend going up to 16-bit scale. And it is possible to, so each CSF file stores your raw samples and your process samples separately. So you can have different compression depending on, or for each one of these lines. And for example, you might want to use 16-bit here and try 8-bit there. I think it's not necessary. If you've got the storage space to do 16-bit, that's what I would recommend. So we've got the sample size. So we're going to use this middle one, this 2048 samples, which will give us 5-centimeter resolution out to about 100 meters. And then the final thing we want to look at here is how we're going to project the data. So there's two options for heading. We can use the course made good, or we can use the sensor heading. Sensor heading only works if you've calibrated your side scan compass before you went underwater, or you have some kind of IMU. Now, in the case of this AUV data that we're going to import, it had a full motion sensor in it, so our sensor heading is really good. But a lot of towed side scans have a compass built into them or some sort of motion sensor, and if they're not calibrated, they're useless. So then we recommend using course made good. You can also do pitch correction, which is more important for kind of pole mounted side scans. It will work for this AUV because we have pitch information. So I guess the key point here is use the smallest value for samples per channel that will produce in a cross-track resolution that you can live with. Because the more data you push through the system, the longer everything takes. So we're going to use 2048 for this sample. So let's bring these guys in and we'll let this load. So here is our mosaic. So there's a lot to see here. First of all, it's a cool data set. There's plenty of stuff to see here. One thing that I can look at right away is we've got lines going in different directions. This makes it hard for a mosaic to look good, especially with side scan. So if a side scan is towed properly, it's down low to the seabed. And so it casts shadows on either side of the transducers. So if you have side scan going in different directions, you get shadows being cast in different directions. And this can make your mosaic look bad. So the first thing I'm going to do here is just turn off this line that is going in the wrong direction here. Turn this guy off. And that will help a little bit. The second thing that we can see here is that the bottom track has these really, well, you have to pay attention to how your data lines up. And so we've got a couple of things that we need to make sure it looks decent. If we open up the bottom track here, it looks to me like, although this data was collected with an interferometer and it has bathymetry with it, the offset of the bathy track line and the actual imagery is pretty, so if we look up here, you can see what the range is. And this one is off by about 1 meter. So it goes from, the track line's at 17.5 meters and the first good pixel is around 18.3. So I think it would be worth retracking this. And before the presentation, I kind of went through and found some settings that work best, and actually our edge detection works really well. And if we re-track this using the edge detection, it does a pretty good job. There might be a few spots in the data set where that doesn't work, but we'll go with that. So I'm going to apply the edge detection and close it. And you can see now that track line kind of closes up and we have data all the way into the center. So let's copy that, or what we're going to do is use our batch bottom tracker here and use edge detection on all the track lines. So we'll just track them all. This will take a second. So what we want to do is try to minimize the errors in the nadir. This can be a source of kind of ugly mosaics. If your track line kind of floats in and out of the water column, as you go down the line, you'll see these little lenses or fish eyes. There's probably little things kind of like this. There's a little bit of it here. And if we had time, this is definitely some where it's gone off. So if we look at, you can see these little fisheye lenses here. If we look at the bottom track, I bet you that it did not do so well down there. So if we come down here to the bottom, yeah, you can see where there was some kind of noise in the water column here, and the track line didn't really stay on the seafloor there. So I'll just clean this up a tad and save it. Let's see if that helped a little bit. Yeah, not enough. Another trick you can do if you have a problem line like this is go into the bottom tracker, and we have this offset altitude, and what that is used for is a situation like this where you've got, maybe you don't have time to go back through and do a real detailed bottom track again. So what you can do is offset the altitude a little bit, say maybe 25 centimeters. And it slides the track line into the data a little bit, and will hopefully push it close enough that it kind of reduces this artifact here. We can apply it and see if it works. Okay, I'm going to close this now. And there, just a little bit of pushing that, using that offset altitude kind of cleaned up that spot here. You don't want to overuse that, because that's basically lowering your fish altitude by 25 centimeters. On a track line this large, where we've got 65, 70 meter range, that's a very small offset to your data, but it does shift all of the pixels inward by 25 centimeters. The next thing you want to make sure is that you've got nice alignment between your overlapping track lines. So if we look at this object, and we've got two overlapping track lines here, and if I select one of these guys and I use our swipe tool, I can see that we've got two track lines going in opposite directions, but they don't line up exactly with each other here. So normally for a towed side scan, this is probably, you need to account for your sheave offsets. So there is your tow point a little bit off center on the boat. Is it backwards on the boat? A real easy way to kind of correct this kind of problem, the simple way and the hard way. The simple way I'm going to use here, we're going to just use a little feature, and I'm going to identify a point on this, right on the center of this rock here, and then I'll turn that line off. And I'll put another feature, right where that rock occurs over here. And then we can measure the difference between those two. We can see that there's a little bit of a horizontal offset, or an east-west offset, and a north-south offset. So this one is in the along track direction, and it's about 4.2 meters between these two points. And then there's maybe a 1 meter offset, port and starboard. So we can go into our sheave offsets here. So let's select this. We'll turn them both back on again. And I go down here to our offsets here, and I'm going to turn on layback calculations. And I'm going to add, so the distance between those was, what did I say it was? 2 meters? 4 meters, 4.2. So that's about, if we divide that by 2, it's about 2.1 meters. So we'll add that to the Y here, 2.1. And I think there's maybe a 50 centimeter offset in the X direction. So let's apply those to all of these files. So we'll just take our offsets and our layback settings and sheaves, that's what I mean. So we've got layback is on, and we have these X, Y, and Z offsets. Now I'll just apply it to all of them. Now as it recomputes here, doesn't look like I moved it in the right direction here. See, I get them all on. Oops, I forgot to enable sheave offsets. So when you have to have both of these check marks. This is actually a common problem. You have to have laybacks turned on, and you have to have the sheaves turned on in order for this offset to work. So I'll go back in here and make sure that I've done it right. Apply all these settings. The sheave computations, and the sheave toe point is basically from your GPS position. You've got a port and starboard offset and a fore and aft offset to the toe point. When you're working with an AUV, the toe point, these are very similar to where the pole would be mounted or where the transducer is mounted relative to your position sensor. So now it looks like we've got a single, nope, it's not quite done yet. There we go. So now we notice, okay, we've still got our original 2 points there, but now our target is right in the center of them, and it crosses correctly. So that's really important. Before you do any mosaicing, you need to make sure your bottom track looks good, and you need to make sure your navigation is good. So when we zoom out, we don't have blurry offsets that are due just to the fact that our track lines aren't aligned. So the next thing I want to talk about is gains. So we can see if we isolate one of these track lines, that there is a strong time varying gain going on. So here at the center, at the nadir area, it's pretty bright. So it's bright, and then it fades away, and then we get very little signal out here. And what we want to do is apply gain so that we get a nice even gain all the way across the track line. So back to our presentation here. SonarWiz has a lot of gain options built in. The most commonly used these days are AGC, Auto TVG, and EGN. I don't have time to go into all of the details of these gain algorithms for this talk, but it is worth noting that they really have an impact on what your data looks like. This survey here is quite large, and I had, this is another customer's data set from a few years ago. And we processed the data using all 3 algorithms so that we could see what they look like. AGC, or automatic gain control, is really optimized for working on small sections of a track line. So if you're looking for targets like a shipwreck or an airplane or something like that, it maximizes the dynamic range of a small area. And it has a tendency to remove geology. And that's the problem when you're making a mosaic. So we took this data set and ran AGC on it. So the settings were the same for every single track line, and it looked like a big gray blob. You can't see anything. The next option was the Auto TVG. And Auto TVG has a bit of a memory, so it corrects the data, but it then kind of remembers over time what its previous correction was. And this helps preserve geology a little bit, but you can see here it kind of acts like an edge detection filter. So it's still overall, everything is gray, but whenever you change geology, so when you go from a rocky reef onto sand, you get a strong gradient there, and so you can see it in the output. And then when you jump back on it again, it kind of gets another edge. So it acts like it's detecting the edges, but doesn't preserve the overall grayscale the way you want it to. EGN was designed to avoid those problems of both AGC and Auto TVG. It tries to build a model or a signature of your sonar and apply that uniformly to all the track lines. And so the pixels get corrected the same way every single line, and it remembers what it's done, and so the pixels in one side of the survey can be compared to pixels in the other side of the survey. And so here you can actually see the geology popping out. So for mosaics where this is your goal, to see geologic features or marine habitat, we recommend using EGN. So let's take a look at that in real life here. So we've got a single track line here, and we go into settings, we'll go enable EGN, and we're going to build an EGN table. So this is usually the first step of EGN. So we go through and we build a signature of our sonar. And the best way to do this is to feed in all of the data in your data set. It has to, there's a couple of restrictions to this. It has to all be from the same sonar system. They should all be operated at the same power and pulse widths if you have control over those, and the same frequency. You can have more than one EGN table in a project. So if you're mixing sonars or you're mixing settings, then you should process each of those separately. But for this, we have 9 track lines and they were all collected at the same time, so we can build a single table to represent all of them. While that's building its table, I'm going to kind of talk about what these tables are actually doing. So here is kind of a conventional view of a mosaic. We've got 4 track lines, 1, 2, 3, 4, and we lay them down on top of each other, and where there's overlap, we average the values together. And why do we average the values where they cover up? And the reason we're doing that is to try to minimize the artifacts that come from the sonar system and show just the underlying geology that's underneath them. If we had enough time, we could survey this hundreds and hundreds of times and average those surveys together. And eventually, the thing that stays the same is the geology. The thing that's different are the artifacts from our sonar. And we would eventually get rid of all of these trackline artifacts, and we would just have one clean view of the seafloor. What EGN does, so the averaging, keeps the things that are the same, which is the seafloor, and it averages out the noise or the artifacts that come from the system itself. Now, what EGN does is it takes this idea and turns it on its head. It says, we will need to find what that noise is. So we need to put this in a reference frame. We take this amplitude data and map it in a way that we can actually see the noise. And we want the geology to be erased. So we take exactly the same data, and instead of plotting it as an XYZ value on the seabed, we plot it on a plot like this, where in this plot, the transducer, the sonar, is up here at 0, 0, and we've taken the amplitudes and we plotted them as a function of depth or altitude and horizontal range. And now, so if we just keep stacking ping after ping after ping up, we eventually build a signature of our sonar system that is very sensitive to artifacts in our sonar. So this particular one was built from a SWAF Plus from 10 years ago or so. And we can see the different, this is the actual pattern, the beam pattern of the system. So it's a side scan interferometer, similar to what we're using an EdgeTech 2205 in this example. So this is kind of similar geometry, but this is an older design. You can see here these beams coming off. And again, this is just data that was collected on the seafloor, but instead of plotting it on XYZ, we're plotting it in this reference frame where it's pinned to the transducer. And by stacking it up, we can see all of the artifacts. Now that we know where they are, we can go back and correct for them. So every time we correct, we go back to the beginning again, we look up a value and say, okay, this particular sample was at 30 meters depth from the transducer and it's 70 meters away. And that's a little bit bright, so we need to tone it down. And in fact, if you look at this data, oops, here, you can kind of see where it's not very bright there, then it gets kind of bright, and then it fades away. And we're seeing that here. It's bright, then it fades away like this. So now we have these corrections. We can take something that looks like this, and when it's raw, and clean it up so it looks very, very clean. So we've done that. Our table's made now. So we've got a table here, and we just need to apply it to our track line. So now it has applied, and it's corrected that offset, and we can, it's gained up these lines. So here, we're going to apply it to everything. So you right click here and say make others like this. And we want to do all settings, but what we're really interested in here is this EGN value. So we're saying every track line use the same EGN table. This takes a second to process. And now it's much better. Even the line that is going the wrong direction has been corrected. And now that it's got good gains on it, if it's almost invisible. I'm still going to turn it off because I think our data looks better without it. And now we're starting to get something that looks pretty good. I want to talk a minute about the colors settings in here because these can be a little bit confusing. When you open up the color window, we see a histogram of all of the enabled lines in our file. So each one of these track lines has plotted its amplitude values here. And down here, you've got the scale mode. So here's where we pick our color map. And I have my own custom version of MSTL bronze I like. And then down here, I've got things set to scale mode all data. So manual is easy to understand. In manual mode, every single track line gets colored from the minimum value to the maximum. So the minimum right now is 107 and the maximum is 3538. I'm not sure what these units are. They're just what the sonar recorded. And you can kind of change how this looks by adjusting that manually. If you're in manual mode, you've got two buttons here. One says scale to data, and that just sets the lowest value at the minimum value. So 9.5 was the minimum that we observed, and the maximum was some outlier at 24,000. So you can kind of see you've got a big tail here. So if you want to get the colors to look the way to look nice, you can just do this manually. That's one way to do it. Another way is to use these auto modes. And auto all data, what it does is it tries to find the best value, usually like the middle 80% of your data for the entire histogram, and applies the same to every single track line. Another useful mode is this auto this data. And what it does is it gives a different mapping to each one of your track lines. Sometimes you've got one track line that is much brighter than the others. If you use this auto this data, it treats that separately. So this track line gets a value, this one, this one, this one, this one, this one, they all get values. And in some cases, especially when you're messing around with the gains for each track line individually, this can help. But since we used EGN and we used it the same on all of them, the auto all data actually looks best, and we have the best match there. So that's kind of a brief overview of what these color modes do. The other thing that affects how data looks in our mosaic is the overlap mode. So if you have it set to shine through, right here we've got an area where two track lines are overlapping with each other. And we have to decide what color pixel is going to actually show through. The different modes here shine through, and in this case, the brightest pixel in the stack shows through, or you can average them together, which is what this does. EGN usually looks pretty good with average. And then you've got cover up, which is a traditional stack where you control the stacking of the different layers. If you get close, you can kind of see an edge. Here's the edge of one line versus the other. Depending on your mosaic, different things look better, but usually for a good mosaic, I think average works best. Or root mean square is another way to take the average. So now we've got our mosaic. It's positioned in the right place, and we're ready to kind of make products from this. So let me turn off anything I don't want to export. So like these feature dots, I don't need those. And let's go into this export dialog. So When you export an image from SonarWiz, what I usually do is just click this fit to window. Now we've got our edges snapped there, and SonarWiz will export whatever is showing in the window. So we have two different output options. You can save the project as a geo image, or you can save it as tiles. If you go to save as geo image, this is where we have kind of a complicated export option. So first of all, you can export these images in multiple different file types. GeoTIFF is the default, but you can also make JPEGs, PNG files, ERDAS Imagine files, bitmaps, and there's several others. Each one of these file types has certain limitations. Even though GeoTIFF is the most common export format, it's actually a really old format, and it has some problems with compatibility between different programs. For example, the largest file you can make a GeoTIFF out of is only 4 gigabytes. So if you try to export a giant bay survey at 10 centimeter resolution, it's possible that it will be too large for a GeoTIFF. You might be able to get away with that with a JPEG 2000. You can have enormous files in some of these other data types. The other thing, stumbling block for people is this bit color resolution. There are 3 options currently: 8-bit, 24-bit, and 32-bit. So if you select 8-bit, what you're going to get 256 values for every pixel in the image. And those values are going to be mapped to a color map. So there'll be an index in the image, and it says color 0 is the background color, color 1 is green, color 2 is red, and so on all the way down. This is a very compact way to export data, and some people like it because I think 0 is always the background color, so you can load this into a GIS and say make color 0 invisible. It's pretty simple to understand. The downside is that if you have this high dynamic range sonar, you only have 256 colors for the entire range, and sometimes that looks a little pixelated. The next option is 24-bit, and this switches the way the image is actually produced. Instead of having just a color map, an index, you have 3 different numbers that represent a pixel. One is for the reds, one is for the greens, and one is for the blues. Each one of those has 256 values, and that's stored as an 8-bit number. So if you add those up, red, green, blue, 8 times 3 is 24, and that's what you get here. Now, a 24-bit GeoTIFF has no way to make a background color transparent. So because there's no transparency layer, all we have are reds, greens, and blues. And unless it can be very difficult, you can't make some of these file formats have transparency with 24 bits. So mostly what I recommend is this 32-bit option. And what that does is you have one channel that's red, one channel that's green, one channel that's blue, and we add another 8 bits. That gets us up to 32. That is called an alpha channel. And that says for every pixel, how transparent is this particular pixel? It's a mask that goes on top. Not all output software supports 32-bit GeoTIFFs, but I think ARC does now, and most of the modern systems do. And this allows you to have background transparency. The next thing I recommend is when you are exporting data, you want to pay attention to what your color map has. So in this case, our color map ranges from black to gold. And see how I've chosen a contrasting color for our background that does not appear in the data. So in this case, it's blue. So you don't want to choose black as your background if black is in your data set, because what can happen is areas like this where there's a strong shadow might be, if they're exactly the same color as the background, then they will get removed from the data set. So before you do your exports, make sure your background is a contrasting color that does not appear in your output. And then finally, we've got to specify an image resolution here. So SonarWiz at this doesn't care what the image resolution is inside the program for display purposes. This is the only place where you actually set that up. And it will tell you here so for a 20 centimeter resolution, our output is going to be 4,546 by 2464 pixels. And you want to make sure that this value is not too large. If it gets more than 4 gigabytes, total value, then a GeoTIFF can't handle it. And you may find that some of your downstream programs have trouble with very large TIFFs or very large JPEGs or whatever. If it turns out you need a 10 centimeter resolution and it's too big for a single image, you need to switch over to make tiles. So for this case, I think we're okay making a 20 centimeter resolution. So we'll export that out. Takes a minute, it opens it up. And if we click full screen, it's actually, oops, it looks really nice. Okay. But you notice it's got these rough edges on here. So something else we can do is add a little feature, a feature in here that will just kind of trim our area of interest. Area of interest. And we can draw a box around it like this, just inside the data. And you might have an actual survey polygon that was provided to you by your customers. So now we've got a survey polygon here. And if we go back into our geo image export, there's this line here. It says crop the image to the area of interest. Let's export that again. You can use different, if you have a river or something like that, where you have a polygon that outlines the river shape, or a port and harbor, you can clip out the individual, keys and piers and that sort of thing. I've just done a square. So now it has a nice, neat edge all the way around it. If you can't export everything into a single image like this, the next option would be to use your mosaic as tiles. And for example, if we wanted to do 10 centimeter tiles, 100 meters by 100 meters, you can click this preview button and it'll show you that this would make 42 individual images. And SonarWiz has drawn in pink here what each one of those images will look like. And this takes a little bit longer to export, so I'm not going to demonstrate it today. It doesn't take that long for a small data set like this. But what you get is a shapefile that represents the map of different tiles, plus you get one tile for each one of these outputs. And you can load the whole kit and caboodle into GIS and kind of click on the tile to have them show up in the right place. But this is the tool you want to use if you have a really large area and you need very high resolution. So the final kind of cool thing we can do with our mosaics is drape them over the top of bathymetry if you have it. So in this case, since this was an interferometric system, we do have bathymetry. So we've got a bathy file here. So I've got some nice bathy that goes with it. And if I add this image that I just created, so we're going to go to maps, add base map, and we'll add our image there. So it file underneath there. What I can do is go to View, Enable 3D, and then, oops, I've got this thing turned on. We're going to show we've got our 3D image here. You can see it's kind of, can zoom in and out here. Select, now we'll go back over here and select our TIFF that we just loaded. And down here in the properties, it says display in 3D. So now our TIFF is kind of floating in space up above our data set here. If we go up here to this small menu, and we select our grid, there's an option here to drape an image over the top of the grid. And we've got our image loaded, so we'll just snap those two together like that. And now we have a perfectly registered side scan mosaic on top of our bathymetry. And we can adjust the vertical resolution there totally.